In the fourth lecture of Pharmaceutical Calculations, we will be talking about proportional calculations and alligations, as well as calculations involving very small quantities, either for solid or liquid. Let's look at the first topic of this lecture, proportional calculations and alligations. So this method is usually applied when we need to prepare formulations with intermediate strength from two similar preparations but of different strengths. So imagine here with this example, if you want to prepare 50% of a solution from a mixture of 10 and 70% of similar solutions. So we will use this double cross principle to do the calculations. First, let's look at this example where you have to prepare 500 ml of an intermediate strength of acetic acid of 16% from 10 and 30% of it. Put them on the double cross principle. So it's either way. From your left panels, it's either 10 or 30, you can put the other side. So but remember that on the left panel is always your original or initial solutions, and at the center you have the final concentrations or the intermediate concentrations, and on the left panel is the subtraction of the number regardless of the size of the number on the cross. So in this case, 10 minus 16 you get 6, and 30 minus 16 you get 14. And another step you have to do is to total up the number on the right panel. 6 plus 14, you have 20. So to calculate the volume you need from 30% of acetic acid, you will need to take the ratio of the number on the right panel, 6 divided by 20, and times with the final volume. And in this case, you will need 150 ml of 30% acetic acid. So the same will happen for 10%, where you're taking the ratio of 14 divided by 20 and times with the final volume, which is 500, you will get 350. So put them into a table form. You'll see that for a final solutions, we will need 16 grams in 100 ml. So for 500 ml, you will need 80 grams, which is just 5 times of the 60 grams. So from the stock solutions, we have the two of them, 10% and 30%. From the value calculated, 150 ml of 30%, we will contain 45 grams. And for 10%, we will need 350 ml, and it contains 35 grams. So total up of these two amounts give you the 80 grams, which fit or match with the amount that we are preparing, which is 80 grams in 500 ml. This principle can also be applied when you only have one initial stock solutions. So in this case, you have to prepare 1500 ml of the 33% acetic acid from 50% acetic acid. So what you have to do, the same, the cross principle, and the second solution is consider having a concentration of 0. So by putting the same number on the left panel and the intermediate at the center, and just minus the number on the cross and total up the number on the right panel, you should get 33, 17, and 50. And by taking the ratio for each of the solutions, you will get 990 ml of 50%, and for the 0%, you have 510 ml. So putting them into the table, for a final solutions of 33%, meaning it has 33 grams and 100 ml, and for 1500 ml, which is 15 times stronger, and you have 495 grams. So let's check back. So for 50% of the stock solutions, you need 990 ml, and it contains 405 grams, which match with the amount needed, because from the zero concentrations, it means that it is a distilled water, or the vehicle you use, it doesn't contain any solute. We move on to the second topic of the lecture, the calculations that involve very small quantity. So bear in mind that the weighing balance has a limit where it can measure accurately. So in these terms, we name it minimum weighable quantity, or MWQ. So the MWQs depends on the instrument itself, but in our practical lab, the MWQ is equal to 200 milligram. First, let's look at the example for calculating small quantity of solid ingredients. In these prescriptions, you have to prepare a lactose powder containing hyacinth hydrobromide of 20 milligrams. So you know that the minimum weighable quantity in our practical lab is 200. So to weigh 20 milligrams of hyacinth hydrobromide is impossible. So first, you take the MWQ to be divided by the small quantity ingredients, and in this case it is hyacinth hydrobromide. So 200 divided by 20, you get a number of 10. So we can do 1 times dilutions with the ratio of 1 to 10. First, we measure 200 milligram of hyacinth hydrobromide, which is the minimum weighable quantity, and times with the number or the ratio of 10, you result in 2000 milligram of the final mixture. So for this mixture A, we need 1800 milligram of lactose to mix with 200 milligram of hyacinth hydrobromide to get a final mixture of 2000 milligram. And then you have to take 200 milligram, again the MWQ of the weighing balance in our practical lab. And in this 200 milligram of mixture A, it contains 20 milligram of hyacinth hydrobromide. And in this final mixture, we would like to achieve a final amount of 10 gram. So we will need to top up with 9800 milligram. So from these calculations, we actually waste 1800 milligram of the mixture. From the previous calculations, we know that with one dilutions, we waste 1800 milligrams. So is that possible that we can reduce the wastage? Yes, of course. So by doing more dilutions, actually the wastage is being reduced. So in this case, we are taking a ratio of 10. In the previous example, it's just one dilution, which is 10. So in this, if it takes 2 dilutions, it means that 2 times 5 or 5 times 2, we can save quite a bit of the wastage of the mixture. So let's put back into the table forms. So we prepare the first mixture, mixture A, taking 200 mg of hyacinth hydrobromide, and times with the first dilution, the number 2, and we get the final mixture of A of 400 mg. And to do that, we need to top up with 200 mg of lactose, and the total wastage here is actually 200 mg, because we will bring 200 mg forward to mixture B, and in this mixture B, it will contain 100 mg of hyacinth hydrobromide, and to times with the second number of the dilution, which is number 5, times with the initial ingredients 200 mg, we will get 1000 mg, And to do that, we need to top up with 800 milligram of lactose. And in this case, again, we will bring forward 200 milligram of this mixture B to the final mixture, and the total wastage is 800 milligram. So for the final mixture, we take 200 milligram of mixture B, where it contains 20 milligram of hyacinth hydrobromide. And in this final mixture, we need 10 gram, so we just top up with 9,800 milligram. So the total wastage here is just 1000 milligram, which is 800 milligram less than the first calculation method involving only one dilutions. So as you can see now that the number of dilutions will save the number of wastage. To demonstrate to you what is happening in the previous calculations involving 2 times dilutions, we will illustrate them in the next few slides. So in the first dilutions, we're using the number of 2, where we're measuring 200 milligram of hyacinth hydrobromide, and to get a final mixture of 400 milligram, we need to top up with 200 milligram of lactose. To perform the second dilutions, we will take 200 milligram of mixture A, and in this mixture A, it contains 100 milligram of hyacinth hydrobromide. And in the second dilutions, we times with the factor of 5, and to get a final mixture B of 1000 milligram. So to achieve 1000 milligram of mixture B, we need to add 800 milligram of lactose. So in this mixture B, we will have 100 milligram of hyacinth hydrobromide. Next, we take 200 milligram of mixture B, where it contains 20 milligram of hyacinth hydrobromide to form our final mixture. So to get the final mixture, we will have to add 9,800 milligram of lactose to get a final weight of 10 grams. And in this 10 gram, it contains 20 milligram of hyacinth hydrobromide, which is needed in the prescriptions. I hope now you are clear with the dilutions methods and why we need to do a serial dilutions to save the wastage. If you repeat the calculations with the ratio of 9 times 2, you will end up getting the same amount of wastage. So it means that regardless of the sequence of the number, the total of wastage will be the same. In this following example, I would like you to attempt your own, and I will guide you in between. So in this prescriptions, you have to prepare 3 mg of sodium phenytoin in a total mixture of a weight of 15 grams with lactose. So first step, you have to divide the MWQ with the small quantity ingredients. However, in this case, you don't get a round number, so it will make your calculations of serial dilution very difficult. So in order to avoid that, you can put your minimum weighable quantity more than 200 so that it will give you a round number. So to achieve 70, you can do 1 or 2 times or 3 times the dilutions with a different combinations of numbers. So I've given you the ways that we will get from these different types of calculations, and you can figure out your own how to perform the calculations as I guide you in the previous example, and you will find that the more dilutions you do and the least wastage that you will get. In this following example, you will have the same problem where you don't get a round number for the ratio. So in this case, you can either increase the MWQ to 210, where you can get this amount of wastage, or to 240, and you will get this type of wastage. So it's actually up to you, but as long as you're able to reduce the wastage for your calculations and preparations, that would be enough. Calculation involving very small quantity ingredients also happens to liquid or solutions. So let's look at this example. If you have a caffeine 50 milligrams to be prepared in a final volume of 50 ml. So how much of the initial stock solutions that you would like to prepare? So I've given you 5 selections here. Whether you want to use to dissolve your 200 milligram caffeine in 5, 10, 20, 30 or 40 ml. So have a think about this before we discuss in the next slide. In this type of situations, what you have to put into consideration is the solubility of the active ingredients. So in this case, given that the aqueous solubility of caffeine is 2% or 2 gram in 100 ml or 220 milligram per ml. So given all the solutions we have and the amount to dissolve is the same, but the volume of water used is different. So you end up a different concentrations. So to make the discussion easier, we would like to convert the current concentrations to in 1 ml. For solution A is 40, 20, 10, 6.7 and 5. So by looking at these situations, we know that solution A has exceeded the aqueous solubility. So meaning that the solutions you get will be opaque because the caffeine cannot fully solubilize. So let's look at the solution B. So in this case, it's just right the amount added is able to dissolve. So in this case, how much do we need to get to achieve 15 milligrams? So you know that 20 milligrams is found in 1 ml. So in 15 milligrams, how much you have? So I guess you can simply calculate and you get 0.75 ml. So you can do the same for the rest, and then you will find that the amount you take is going to be increased. So in this case, all this volume is smaller than 5 ml. So you have to use a pipette to withdraw the volume. So the amount or volume to be taken depends on the solutions you're going to prepare. So how much of the water you need to get to your stock solutions depends on the final volume of your final formulations. So if you dissolve your active ingredients in a bigger amount of vehicle which exceeds the final volume, then you will have a trouble. So it's advised that you try to use the minimum amount which is able to withdraw accurately with your equipment in the lab. That's it for the discussions for proportional calculations and alligations, as well as the calculation involving very small quantities of ingredients. Thank you.